In this video, we are going to have a look at the second derivative. And the second derivative of a function, this can really help us understand the shape and curvature of a curve. It can also help us prove if a certain turning point on our curve is a minimum or a maximum. Okay, so the second derivative is a subtopic part of differential calculus. It's in topic 5 and it's in the applications and interpretation, the AI HL course. Okay, so what I really want students to understand firstly is the difference between a function, the first derivative, and the second derivative. So if I said we know that y is equal to some function of x, and we have an example up here. Our function of x is x cubed minus 3x squared minus 9x. Well, f of x, our function, if we just substitute in a value for x, we would get the output, which would be the y value. So this will give us the y value on our function. Okay, that's what the original function will help us find. But if I find the first derivative of a function, and hopefully by now you've learned how to find the derivative of different functions, but what the first derivative helps us find is the gradient or the slope, which is the same word, at a certain point on our function. So what the first derivative helps us find is the slopes or the gradients. And this is often written as m for gradient. Okay, so the first derivative, it's really helpful if we substitute in any value for x into the first derivative, the output result is m. It's the gradient of the curve at that x point. Now the second derivative, which is the f double dash here, you can think about this in a few different ways. The second derivative is the first derivative of the first derivative. So it's the derivative of the first derivative. So therefore, this can be considered as the slope of this here, the first derivative. That gets a little bit confusing when you're treating the second derivative as the slope of the slope, because the first derivative was the slope of the original function. But more commonly, you'll often more commonly see that the double derivative helps us find or information about the curvature of the original function. Okay, so these are just really basic descriptions of what the first derivative and the second derivative can help us find. The first derivative can help us find the slopes and the gradients of the original function, and the second derivative can help us find and understand the curvature of the original function. Okay, so hopefully that makes a little bit of sense. I'm going to use an example here to really try and make some sense of all of this. Okay, so let's rub all this out. We have our function defined up there at the top right-hand corner of our screen. What I'm going to do is find the first derivative. So the first derivative will be equal to 3x squared minus 6x minus 9. Now, as we said, the first derivative, very helpful, because if we substitute in any value for x, we will find the gradient at that point on the original curve. Now, if, for example, we wanted to find the turning points here and here, let me get my red pen here to show these turning points. This is the local maximum. This here is the local minimum. Well, what we learned when we found the first derivative is that at turning points, at these points here, the gradient, the slope is 0. Right here, we know that if we draw a tangent line, the gradient m is 0, and likewise here. So if I want to find when the gradient or when the slope is 0, what we would have hopefully have done by now is we can let the first derivative equal 0 and solve for x. And that'll tell us the 2 times where the slope did in fact equal 0. Let's just quickly do that in green. Let me do it down here. If we let 0 equal this quadratic here, what we can do is we can factorize out the 3 and actually divide both sides by 3. So I'm going to factor out the 3. We would have x squared minus 2x minus 3. I could then divide both sides by 3, and that would essentially disappear. And if I solved for x, I would be solving this quadratic equation. I would have x, this would be x minus 1, actually no, x minus 3. This would be x minus 3, and x plus 1 if I factorized, and therefore our solutions would be x equals 3 and x equals negative 1. And you can check that. There's a few different ways to solve a quadratic. But what our answers here show is that we had the slope, the gradient equaling 0 at these 2 points. And these, as we can see, correspond to points on our graph. When x equaled negative 1, we have a turning point. And when x equals 1, 2, 3, here, 3, we have a turning point. Now, the second derivative, what we can do is we can prove that this here is in fact the x-coordinate of our maximum, and this here is the x-coordinate of our minimum, or local maximum, local minimum. And because we know the second derivative helps us understand the curvature of the original function. Let's find the second derivative here. I know that the second derivative will just be the derivative of this up here. This will be 6x minus 6. And what we can do is we can substitute in these x points, these x coordinates, into the double derivative. And let's see what we get. Let's firstly find the double derivative of x when x is negative 1. I'm going to substitute in negative 1, one of the answers that we found here. And we will get 6 times negative 1, which is negative 6, minus 6. So negative 6 minus 6 is negative 12. Okay, let's do the other one. The double derivative when x is 3. And what do we get if we do that? Well, we would get 6 times 3, 18, minus 6, which is positive 12. Now, what this answer here gives us some information about is if the double derivative at any x value is negative, that means it's concaving down. That's the really important step here. If the double derivative is negative, we can say that it's concaving or concave down at that x coordinate. And because when we go to where x equals negative 1, what we can see is this is concaving down. Concaving down is an unhappy face, if we were to picture smiling or unhappy. But likewise here, the second derivative when x equals 3 was positive. And if we get a positive value for our second derivative, it's concave up, concaving up at this point here. And this is, often you'll hear, this is referred to as the second derivative test. If we need to justify or if we need to show that a certain stationary point or a certain turning point is a maximum or a minimum, we just substitute those values in to the second derivative. And if it comes out as a negative number, we know that at that point, it was concaving down and therefore a maximum on the original curve. And if it comes out as, if we substitute in the stationary point and it comes out as a positive for our double derivative, we know that at that point it was concaving up. Okay, so this is one way we can prove if something is a maximum or a minimum. Now finally, the second derivative is also very important to find the point of inflection. And the point of inflection is the point on the curve where the curvature, which we know is we can find information about the curvature with the second derivative. When is the curvature 0? And that's the point of inflection. And if you picture our curve here, all the way from here, all the way to approximately about here, let me just draw this in yellow. I'm going to highlight this. It clearly is curving down. It's all part of an unhappy face. But then after that point, let me try and find a different pen here. I'll go a nice blue highlighter. Here it's curving up. It's part of a happy face. And where it changes, which will be this point right here, this is called the point of inflection, or POI for short. And the point of inflection occurs when the double derivative is equal to 0. So that's another reason why the second derivative or the double derivative is very helpful. It helps us find when a curve turns from having a positive curvature to a negative curvature. Okay, so this is a very interesting topic. I do recommend you explore this further, but this is a quick video to introduce the second derivative.